Now all preparational work is done, and I want to survey a proof of the fundamental theorem of arithmetic. The theorem itself, this is theorem 1.8 in the book, tells us that every integer except zero and plus or minus 1 can be presented as a product of primes in an essentially unique way. First of all, let me make comments about what essentially unique means. We can write an integer as a product of primes and is p1, p2 up to pt, and we can write same integer possibly in a different way also as a product of primes q1 up to qs, or pi's and qj are primes. They may, and frequently do, repeat. Doesn't mean that one prime appears only one time. So these two presentations are essentially unique, means the total number of factors, every factor is a prime, not a power of prime. The total numbers of factors are the same. So the first claim is T equals S, and so the two presentation implies if I write it in two ways, that implies T is equal to S, the total number of factors is the same, and possibly after reordering, we have that P I is equal not exactly to qi, but to plus or minus qi. So we rearrange factors, the amounts of them are the same, and we can rearrange them such that P1 and Q1 are the same thing up to a sign, P2 and Q2 same up to a sign, and so further up to P last is equal plus or minus Q last. As an example, consider the integer 12. 12 is, of course, 2 times 2 times 3. This is a product of primes. At the same time, this is the same thing as negative 2 times 3 times negative 2. Or same thing as negative 3 times 2 times negative 2. So the amount of factors is the same, they are somehow rearranged, and we can throw in negative signs. Of course, the parity of the total number of negative signs is also invariant. So we compare these two, this one and this one. We see negative 2, negative 2, negative 2, 2, 3, negative 3. They match and they are the same. So all these presentations in a sense are different, but I would say they are essentially unique. This is the unique, what kind of uniqueness we consider. What does it mean? That all presentations are essentially the same. And the proof of this theorem naturally splits into two parts. So for the proof, we need first every integer except 0 and plus or minus 1 can be represented or presented this way. And secondly, we need to prove the uniqueness in the sense I've just explained. The first part of the proof is, in a sense, simpler. So first, our ability to present every integer as a product of primes follows from the well-ordering principle. We consider the set of all integers which cannot be presented in this way. with that exception, without 0 and plus or minus 1, which cannot be presented. In this way. We want to prove that S is empty. If it is not, otherwise, the set of absolute values of integers in S. Oh, sorry. As a minimum element, the smallest element, and this element this cannot be a prime. If it is not a prime, it is divisible by, cannot be a prime, because otherwise just one prime already presented as a product of primes. It cannot be a prime, so it is divisible by smaller numbers. We present this element as a product of smaller numbers. If these smaller numbers can be presented as products of primes, then this was not the smallest element. If they cannot be, if these smaller numbers cannot be presented as products of primes, this is not the smallest element. If they can be presented in this way, then we multiply them and get a presentation for this smaller element. So these cannot be elements of S. They are smaller than the smallest. In S. Thus, can be presented as products of primes Then, however, this element of S can also be presented as a product of primes. This contradiction proves that every integer with these exceptions can be presented as a product of primes. Roughly, this is how the argument goes. It uses nothing but well-ordering principle at the very beginning. All preparations we made were for the uniqueness clause of the theorem. For that, let me just show the structure of the proof. I will skip details, otherwise you will not see what was essentially used here. I will refer for details to the book. So we started with Euclid's lemma, which allowed us to make division. So for two integers, a and b were integers, b different from 0, we found that we always can divide a by b with the remainder. A is bq plus r, can be presented in this form with remainder which is non-negative and smaller than b. Euclid's lemma allowed us to prove an important property of the greatest common divisor. So with Euclid's lemma, we proved alternative characterization of the greatest common divisor. Namely, greatest common, this was the proposition which we proved that the greatest common divisor of two integers, not both zeros, is the smallest integral linear combination. The smallest positive That was the smallest integer of the form AU plus BV with U and V integers, the smallest positive integer of this form. That proposition allowed us to prove theorem 1.4, that alternative characterization of greatest common divisor was instrumental in the proof of theorem 1.4. A divides BC and AB, the greatest common divisor, is 1, imply B divides C. After that, we specialized that when the divisor is prime, and that was theorem 1.5. P prime P divides BC implies P divides B, or P divides C, or both of them. And that is interesting part of theorem 1.5, more important part of the theorem. And from here, it is just an kind of inductive argument to corollary 1.6. The argument itself, you can read in the book. It is an easy generalization of theorem 1.5. P a prime, and P divides a product not of two integers, but of many integers, A1 times A2 dot 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 A n, implies P divides one of them. P must divide at least one. P divides AI for some I. Or other way to say that, there exists an I such that P divides AI. Anyway, P divides product of many integers, implies P must divide at least one of them. Now, that's all. From this corollary, uniqueness, as I formulated that essential uniqueness, follows more or less automatically. You write these two presentations. Look, this is the same number, so the two products are equal. P1 PT is equal to another product. P1 divides n, P1 divides this product. P1 divides this product, it must divide one of the factors. These factors are all primes. Prime divides prime means they must be equal up to their signs. We found P1 in this product. Let us cancel it and look at the next prime P2. Again, it is here. You may do it other way around. Take Q, and because Q divides N, you are able to find that Q divides one of the factors. The factors are primes. So Q up to sign is equal to one of these primes. That procedure will eventually stop. You just cancel equal factors. The procedure must stop, and at this moment it cannot happen that you still have several Q's, but you run out of P's. Because then the product of several Q's is going to be 1, which is impossible. It's definitely bigger than 1. Manifestly bigger than 1. They are all primes by absolute value bigger than 1. That's it. This is the way to prove uniqueness. Thus, uniqueness by this argument is implied by Euclid's lemma. As soon as we know Euclid's lemma, we can try to mimic this argument. And that is what we're going to do later with some different objects. In fact, this is more or less a paraphrase of the proof given by Euclid more than 2,500 years ago. So he realized that the fundamental theorem of arithmetic is not an experimental fact, but can be derived from simpler properties of integers. That is Euclid's proof, which in this class we will deal with later again. With that, chapter 1, which was devoted to arithmetic and Euclid's lemma and Euclid's proof of the fundamental theorem of arithmetic, is done. Thank you for listening.